So I want to go ahead now and complete those last two questions from chapter 4. These involve friction, so let's get into it. I'm going to start with number 37 out of chapter 4. So here it tells you that 35 newtons of force is required to start a 6 kilogram box moving across a horizontal concrete floor. And they want to know what is the coefficient of static friction, right, between the box and the floor. And so static friction is the friction necessary to overcome, well, it's the friction you need to overcome in order to get an object into motion. So it's what's keeping you still. Again, we'll do a free body diagram here. So free body diagram, right? I'll go ahead and create a coordinate axis here, XY coordinate axis. As usual, place the mass as a point mass, or imagine it as a point mass right at the origin. And then go ahead and highlight the forces. So we have obviously the weight pointing down, right? Gravity down, mg. And then we have the normal force pointing up, and those should be equal and opposite because this thing is not moving up or down at all. It's in static equilibrium in the y direction. We're told that we need 35 newtons of positive force. So 35 newtons, I'll just call this the F applied, let's say, the applied force in that direction. And this is going to be resisted by friction, right? So there's a frictional force like this. And so friction is generally given by lowercase f. And since we're dealing with static friction, we do it lowercase f with an s. So for part A, right, motion occurs when this happens. Basically, when the sum of the forces in the x direction is greater than, strictly greater than 0. So what's happening here? Basically, what I want is my applied force, right, to be greater than my static friction, right? That's basically the idea. When that happens, then you move. And we're given the applied force, right? We know that's 35 newtons. Now, it's all about the static force, right? Because we're looking for the coefficient of static friction. So static friction, F static, this is equal to the static coefficient. So this letter here is the Greek letter mu, mu. We put a little s for static. It's a number, and it's between 0 and 1. And basically, the closer it is to 1, the greater the friction. The closer it is to 0, the less the friction. And it has no units. So it's the static friction equals that coefficient of friction times the normal force. In this particular case, the normal force is equal to mg, right? So the static friction is going to be mu s times mg. And we're going to take that, and we're going to sort of plug it, we're going to take this, and we're going to plug it in there. So what we're going to find out is that the applied force, right, must be greater than mu s mg. So now we can go ahead and solve for mu s, right? We can just divide both sides by mg. And here what I'm going to do is I'm going to say, well, it's roughly equal to, right? Basically, strictly speaking, it's greater than, but we're looking at sort of the instant when it hits this. It's kind of a hand-waving approximation, but anyway. So if we go ahead and we do that, right, we're going to say mu s, right, I'll divide both sides by mg. So let's say that mu s is approximately equal to the applied force over mg. Right, the applied force is 35 newtons, right? That's the force that gets this thing moving. We know it's 6 kilograms, and we know that g is 9.8 meters per second squared. And we'll see what this number is, right? So this is going to be newtons over newtons. So it's 35 divided by 6 times 9.8. And I get, when I go ahead and do that, 0.60. Right? So that's the coefficient of static friction. Now, for part B, basically what's going to happen is that as soon as you start moving, the frictional barrier drops. It gets smaller, right? So once you're in motion, it's smaller, and basically you have less friction to overcome. So for part B, it's no longer static friction. We're in motion. So what we can say is that the sum of the forces in the x direction equals max. So what forces are acting in the x direction? Well, the only major difference, right, the only difference is that this would no longer be static friction, but it would now be kinetic friction. So I put like a K there, because now you're moving. So there's a new frictional barrier. So in the x direction, it's going to be the applied force minus the kinetic friction. And there is net force, right? So it's going to be F applied, right, minus the kinetic friction equals max. But of course, kinetic friction, just like the static friction, is the coefficient mu times the normal force, which in this case is just mg, like that. And so we could do the algebra, right? We could basically, if you go ahead and do the algebra, what you're going to find is that the kinetic friction, oops, I made a mistake there. The kinetic friction is the applied force minus max all divided by mg. So if you sort of work this out and just solve for the mu k, you should get the same thing. Let me just double check my work, make sure I didn't screw up. That's right, okay. So now we just plug numbers in, right? So this is 35 newtons minus 6 kilograms. The acceleration, forgot that. Let's see, they say for part B, our acceleration is 0.6, okay. So actually exactly what our coefficient was, 0.6 meters per second squared over 6 kilograms times 9.8 meters per second squared, like that. So if you go ahead and plug all that stuff in, you get 35 minus, that ends up being 3.6, divided by 6 times 9.8. You get a grand total of 0.53. It's smaller than the static friction. It should be, because kinetic friction in general is smaller than static friction. Okay, last problem. Here, we have an icy day and you worry about parking your car in your driveway, and the driveway has an incline of 12 degrees, and your neighbor's driveway has an incline of 9, and the driveway across the street is at 6. The coefficient is between the tire and the rubber is that. Which driveways would be safe to park in? So the goal here, this is important, we're going to be doing the incline plane. So again, we're going to do a free body diagram. But life is a little more interesting here, actually. So what we're going to do is I'm going to draw this free body diagram, but I'm going to do it at a tilt, right? So what I'm going to do is imagine that here's my axis, right? That's my x-axis. And the beauty of creating a coordinate system is you can angle it however you like. So I'm going to create my axis there. So I'm going to tilt my axis. And I'm going to make this my angle theta. This is the Greek letter theta. It's usually just used to represent an angle. So what's happening? Well, this is my car. It's kind of hanging out there. What's happening? Well, gravity points straight down, right? It points straight to the center of the Earth. So it's not a great picture. Let me do that a little better. That's my mg. It points straight down. But the car, this is the driveway, and the normal force acts perpendicular to the surface, right? So normally, the normal force and gravity were just equal and opposite, but here they're not going to be, because the normal force is up like that. And basically you can demonstrate, I'm not going to go ahead and prove it, but you can prove that that's theta as well. And then you can kind of go ahead and do a bit of fun geometry here and kind of create a right angle, a right triangle like that. And so so what ends up happening is that the hypotenuse is mg. This side here, it's opposite, so it's sine. That's mg sine of theta. And this side here is adjacent to the angle, so that's mg cosine theta. And then there's also static friction, right? Static friction is keeping this thing up, is preventing it from sliding down, so we have static friction like that. Okay. So there's a lot going on there. So basically the first thing to realize is that normally, right, the normal force is just mg. But in this case it's not, right? Because all of the weight, remember the driveway is reacting to the weight vector, right? But the driveway, the weight vector, not all of it is directed into the driveway. Some of it's directed down and some of it's directed into the driveway. So the piece that's directed into the driveway is mg cosine theta. So this piece here, like this piece there, right, that cancels out or balances out that piece. So what I could do is we can say Fn, and this is true for the inclined plane. So the normal force on an incline is mg cosine of theta. Right? That's a sort of important thing. Then what we'll do is we'll look at the x direction, right? What we want is the sum of the forces in the x direction to be 0, right? Because the x direction is down like this, right? This is the x direction now. Oops, that's x. And we don't want it to move in that direction, right? We want it to be static. So we want it to be 0. So what's happening in the x direction? What's pulling it down? Well, this piece, right, the weight, the x component of the weight is pulling it down. And what's resisting it is the static friction. So what we're going to have here is mg sine theta is trying to pull it positive along the x-axis, minus static friction, right, equals 0. But static friction is mu times the normal. Right, so mg sine theta minus mu s times the normal force, but the normal force is mg cosine theta. Right? It's not mg here because of the tilt. And so the m's cancel out, right? There's an m in both spots. So that m goes away, that m goes away. That's good because you were not given the mass of the car. And so do the g's, they go away. And so what you end up with is a nice little relationship like this, that's sine theta minus mu s cosine theta equal to 0. And so you can find the mu s, right? So mu s, if you isolate mu s, which is not too hard to do, you're going to get that it's the sine theta over cosine theta. Cosine theta. And this is tangent of theta, sine over cosine. So you get this nice relationship that this is the case. Right? That mu on an inclined plane, that sort of critical static coefficient is tangent of theta. You don't need the mass, doesn't matter. And we're given 3 angles, right? We're given 12, 9, and 16, right? So basically, the bottom line is that if mu is greater than mu s, it's safe, right? Because you're not going to move. And if mu is less than mu s, it's not safe. You're going to slide. There's not enough friction. And so we can go ahead and do these, right? What did I say it was? 9, 12, 6, 9, and 12. So let's just go ahead and we'll do these. So tangent of 6 degrees, tangent of 9 degrees, and tangent of 12 degrees. We'll calculate all of these, right? These are all equal to mu. Call that mu1, mu2, mu3. Let's see what that is. So the tangent of 6 degrees, right? That's going to be 0.11. The tangent of 9 degrees, that's going to be 0.16. And the tangent of 12 degrees, that's going to be 0.21. So we need, if you go back to the problem, right, the critical one was 0.15, right, the coefficient of static. So whatever's bigger than that works. So this one doesn't work, no good, but these are both good. So these 2 driveways are safe. And that's how you do that, right? So that's the idea for that. So anyway, I hope you found it pretty useful. There's a lot of questions now. You can work on those and use them as a guideline. And obviously the book has lots of sample questions too. Reasonably good book, I think, with a lot of good examples. Okay, reach out if you have any questions.